Very good morning, ladies and gentlemen. A very warm and cheerful welcome to the day 3 of Qiskit Fall Fest 2025. And a very warm welcome to all our respected faculty members, dignitaries, guests, and the ever enthusiastic participants, of course. It's a brand new morning filled with fresh energy, sharper curiosity, and that some spark of innovation that has carried us through this incredible fest. Each day has unfolded, hopefully, a new dimension of learning, and today promises to be another exciting stride into the future of quantum learning. And before we begin, let me give you a quick glance at today's power packed schedule. We'll be starting our morning with a workshop session led by Dr.Jnan Yalla, CTO of Data Tech AI and a quantum machine learning and hybrid algorithm researcher. He will be guiding us through the concepts of quantum computing and quantum circuit compilation, continuing the wonderful learning experience we began yesterday. Following that, we'll have an in-person guest lecture on quantum circuit compilation by Ms. Janani Ma'am, quantum engineer at IBM Quantum Research, Bangalore, an expert known for her practical approach to quantum research and innovation. Then you'll be having a refreshing lunch break. Post lunch, we'll have the honor of hearing from Dr. V. Bhujangrao, former NSTL director, who will share his deep insights and experience from the scientific and defense research domain. And to conclude our exciting day, we'll have a virtual guest lecture by Professor Elias F. Combero, full professor at the University of Oviedo, Spain, and former member of CERN, speaking on quantum machine learning and its applications. A truly global perspective to end the day on a high note. So, yes, day 3 is completely packed with knowledge, innovation, and inspiration from some of the brightest minds in the quantum world. Yesterday's exploration introduced us to the fascinating world of quantum computing, from logic and classical concepts to the mysteries of qubits and superposition. And now, without any further ado, let's begin our first session of the day, the workshop session on quantum computing led by Dr. Jnan Yalla. So, participants, get ready to open your minds, tune in with curiosity, and immerse yourselves in this journey of quantum discovery. Let's welcome Dr. Jnan Yalla with a huge round of applause as we kickstart day 3 of Qiskit Fall Fest 2025.
Kuch- Good morning, everyone. I hope I am audible. Yeah, cool. I'm audible. Nice. Okay. So, yes. Um, just wait a minute. Yeah. Okay. So, yeah, first of all, again, a very good morning to everyone. I'm Gnan Yalla, and yeah, as you already know, yesterday itself we started our session. So, yes, in today's session, I'll be going forward with some more like concepts in quantum computing, or yeah, quantum computing technically. So we'll be starting with some of the logics of quantum physics, like even more logics of quantum physics, which is very useful for quantum computing and quantum circuits and all this stuff. Okay, so yesterday we mostly had a session on something like why quantum, what is quantum, and how we can, why exactly do we need quantum, and some of the base states, like some of the basics of why quantum and how quantum works technically to speak. Now, in today's session, first we'll be starting with some of the mathematical concepts, like which are exactly required only for quantum computations and stuff. And then, with the help of those logics, we will try to establish quantum circuits and quantum gates and how an exact quantum computation will happen. Meaning, completely converging or completely going to quantum computing from our quantum physics or quantum mechanics. Okay, so that will be the basic deal of today's workshop and today's concept. That's the basic gist of it. And in order to address some of the like queries of yesterday, I like to say, like, if you want to learn quantum computing, or if you want to be like a quantum physicist, or no, not exactly like a quantum physicist, but more like a quantum computing scientist or someone, it is not mandatory for you to be a pro physics guy. Okay, it is not mandatory. That depends on the thing which you are actually going. For example, if you want to be a quantum scientist for quantum materials or quantum sensing, at that time you need to have huge physics knowledge. Why? Because you will be dealing with materials. Materials have a lot of properties and you need to know everything. Other, if I want to be like a quantum machine learning engineer or quantum machine learning scientist, I don't need to keep my mind that much on quantum materials. Okay, so that's why I don't need that much knowledge on quantum materials or material properties, thermal properties, and all those stuff. Then, if you want to go to quantum communications, you need to have huge mathematical knowledge on how your actual communications and protocols work. For all these things, it is not mandatory that you should be a pro in physics. Pro in physics meaning you know magnets, you know electrics, you know kinematics, you know nuclear physics, should know everything. But it's not mandatory. Okay, it is not mandatory to be a quantum scientist. Okay, so that's a basic thing which I want to tell to everyone. You should focus on the aspects which you want to go through. For example, quantum machine learning engineer concentrate more on optimization or Hamiltonian equations or energy equations and stuff like that. Quantum communication and quantum cryptography focus more on mathematics behind communications, networks, protocols, signals, waves, and those concepts. So it works in that way. You don't need to be a complete physicist guy. Okay, that's the first thing which I want to tell. Just keep this in your mind so that you don't need to lose motivation. Else, yesterday I just listened this a lot or heard this a lot. Most of the people came and they were like, "I am not a physics guy, or I am not into physics. Then how can I be this quantum guy?" At that time, I answered the same question. So that might be there for everyone or most of the people sitting here. So that's the reason I'm just addressing it. Okay, now you don't need to be a pro physicist in order to be a quantum guy. Now, now let's actually dive into today's session. What was the last topic of yesterday? I forgot. That's why I'm asking. Dot product, huh? Okay, I was just kidding. I remember. Now, so the last topic was yesterday is we dealt with something called as a dot product. Okay, so that dot product can look like this, approximately. Not approximately, is known as an inner product, which is nothing but the complex version of dot product. So this is the thing which we've seen in the yesterday session, the last one. And I also told you what an inner product gives. So what is the value of an inner product? How it will be there? It will be like what? A1 star B1 plus A2 star B2 plus so on up to AN star BN. NO, MO, AO, BO, CO మీ ఇష్టమైన వాడుకోవచ్చు, ప్రాబ్లం ఏం లేదు. So this is the inner product. Okay, and this inner product gives me a value which is known as a complex scalar. That's also an important thing which you need to remember, which I mentioned as well. Complex scalar. This gives a complex scalar. Okay. Okay, this gives a complex scalar. Now let's actually take care about this in a more detailed way. So when I was mentioning about Hilbert space yesterday, I mentioned one important thing. What is the concept which I mentioned? First thing is it's complete. Okay. Second thing is that it has inner product norms. Okay. Meaning every vector in a Hilbert space has an inner product. Okay, that's the first thing. Every vector in a Hilbert space has inner product, meaning we can find the inner product of the stuff. And one more important thing is the norm, the concept called as norm. Okay, because it has inner vector norms. NORM, norm. Inner vector norms. So what exactly is this norm? So from here we're going to start the new concepts of today's session. So it already we have already completed this yesterday itself. So from today it's from the norm. So what exactly is norm? Now, sorry. Okay, my bad. I just need to get habituated. Cool. So what exactly is a norm? For example, let's take a vector. Okay, let's take any vector. Like normal. Don't be like quantum or whatever. Just a normal vector. Normal kinematics lo vector untundi. Just a normal vector. Let us consider a vector called A. So how a vector looks like? Let us consider three-dimensional vector. Yala untadi asala? So approximately I can take like A1x plus A2y plus A3z. Okay, so I'll just keep a caps on everything. If you want, you can keep I cap, J cap, K cap as well. You wish, completely alright. I just want to determine it by the coordinates. So this is how a normal vector looks like. A basic vector. This is a vector. If I say norm of this vector, what is the meaning behind it? Okay, norm light. What is the magnitude of this vector? Remember magnitude? Kinematics? Yes, that one only. So you will define magnitude of a vector like this. Yes, I hope, right? This is how we define a magnitude of a vector, which is equal to root of a1 square plus a2 square plus a3 square. Right? This is the thing which we did, the magnitude of a vector. What exactly is this magnitude determine? What exactly does this determine? We know about magnitude of a vector. Cool. What exactly does this mean? If I say the magnitude of this vector is phi equal to phi and theta, what is the meaning behind it? Correct. The length. Yes. So this determines the length. So the magnitude of a vector always determines something called as the length of the vector. The length of the vector. Now, similarly, the same thing. For example, if you take the magnitude of a quantum state. So in yesterday's session, I have clearly mentioned that quantum states, everything exists in where? Where does they exist? It is exists in Hilbert space. Okay. So Hilbert space, may we have vectors. That's the thing, that n-dimensional vectors we have. Okay. So if you take the magnitude of a quantum state, meaning when you take the magnitude, I'm just writing a mag, Don't worry or anything. I'm just writing as mag. Okay. So when you take a magnitude of, the real meaning is if you take a magnitude of a vector in a Hilbert space. Okay. The real meaning is if you take a magnitude of a vector in Hilbert space, I will determine the Hilbert space like this. Okay. H పక్కన ఒక line. Hilbert space. Okay. So a weird H with a line. Okay. If you take the magnitude of a vector in a Hilbert space, I will call it as norm. Simple thing. Okay. Very straightforward. Don't need to think that much. Direct one. For a classical vector, meaning a vector in a coordinate space, let us consider a vector in Minkowski space or whatever, a vector's length is determined by magnitude. Similarly, if you take the magnitude of a vector which exists in a Hilbert space, meaning it can be complex as well. Okay. So Hilbert space may you have complex vectors. That's what we see in a star. Okay. So if you take the magnitude of a vector in a Hilbert space, then I will call it as a norm, simply to put. Okay. That's a basic deal behind the norm. Now, how this norm can be exactly? Let me do some practicals. No. Okay. Okay. So how this norm looks like? Same deal. There's no that difference or something. Directly it looks like the same thing. Okay. So you don't need to think anything. Now let us directly dive into quantum. Now, if I'm talking about the quantum states, okay, let us consider a state called psi. If you take this thing, if you take the inner product, or if you take the inner product of a quantum state, and if you just keep this is known as the norm of the quantum state. Okay, and the norm of the quantum state is always equal to 1. Why it always equals to 1? Because it is probabilities. Okay, if you take each and every coefficient of a state, quantum state, they determine the probabilities. The square of them determine the probabilities. That's what we saw in yesterday's session. Remember? How does this looks like? Yes, correct. Alpha 0 plus beta 1. Alpha and beta determines what? They determine amplitude. Okay. They determine amplitude. What is probability? Alpha square determines probability and beta square determines probability. Now can you tell me why this thing is equal to 1? Why? Because if you take a dot magnitude, let's go back to the magnitude. Forget about norm. Let's go back to the magnitude. If you take the magnitude, you're simply doing this thing, right? If you take the magnitude, we are simply doing this particular operation. What is that operation? It's nothing but, let us consider, it's nothing but this one, right? For example, a square plus b square plus so on. Is this the operation we are doing for magnitude? Right? Now do the same thing for this one, for a quantum state. It will be like alpha square plus beta square plus so on. Like how many states it has, that much it can be. Now let us consider only alpha naught plus beta 1. For alpha square plus beta square, that's it. What is alpha square plus beta square? What is the value of alpha square plus beta square? It's a sum of probabilities. Alpha square is a probability, beta square is a probability. So sum of probabilities is always equal to 1. So root of 1, yanta 1. Okay, that's a simple deal, and that's why the norm of a quantum state, is always equal to 1. This one. Okay, now let us not consider the same quantum state. Let us consider different quantum states. Let's go with the different quantum states. Two quantum states. Now how will it be? So everyone understood till here how the norm of a quantum state will become 1 just because of the probabilities. Just because of the concept of probabilities, it will be equal to 1. Just add them up, it will be 1. Now, let us consider another thing. That is about your different quantum states. Let us consider different. Let us consider two quantum states. First quantum state looks like my psi, sorry, and the second quantum state looks like my phi. Okay, let's consider two quantum states. I don't want to derive the formula. If you want to derive, you can derive. Like for example, now if I take the inner product of this one, how will it be? It will be something like this. So what will it be? The same formula. The same formula which you write. So it will be something like this. 1 star into this one plus so on up to n star psi n. Okay, it will be like the same thing. Okay, this is the inner product. Now if you want to do the norm of this one or something, you will be simply be like square it off. Okay, not a problem, completely all right. But okay, so this is not a formula, but yeah, but that's the main deal of the norm. Now let us directly consider what does this determine in a quantum state. Quantum states, we are talking about quantum states. That's why we are having the inner product. Else we can normally take the magnitude itself, not a problem. Now, when you are dealing with the quantum state, if both the states are same, then it is equal to 1, which we have seen right now. Right? Probabilities untai multiply so 1. Okay? If you take two quantum states, like different quantum states, then the probabilities of this one is different and this one is different. Yes or no? The probabilities of two of them will be different. Right? One will give rise to its own probabilities, the second one will give rise to its own probability. So both are different. In that case, what does this determine? Simple, just have an idea of it. It determines this guy. What does it determine until? See here properly. When I take this, when I'm considering a square, okay, this determines something known as the probability of observing, or the probability of psi changing to phi. That's a simple deal. Okay, the probability of the quantum state psi changing to the quantum state phi. So that is the meaning behind this one. Okay, a simple deal, just keep that in your mind. For example, if you have two quantum states, phi and a psi, this formula determines this particular thing. Remember this thing exactly. If you change them, the formula will be different and it will be gone. That's why write it perfectly or keep this in your mind perfectly. The deal goes like this. For example, when you take phi slash of psi, the meaning is conversion of psi to phi. Okay, the probability of state psi changing to state phi. That is the value of this one. Got it? Understood? This is a simple deal behind it. Got it, everyone? That's it. Not even any case. Now, if you want to actually find the measure of this one, I want to find the measure, bro. Because if you are having the same quantum state equal to 1, okay, measure అయిపోయింది picture item. Now, if you are having multiple quantum states, I have two quantum states here, and I'm saying that if I find this actual value, the meaning is that I am finding the probability of the psi state changing to phi. Yes or no? I am finding the probability. But what is the actual measure? How can I find that? Same old rules and same old stuff only. But it is a different concept. Okay? Concept and theory is same. Okay, the entire theory is same and entire stuff is same. But the only thing which is different is the actual measurement, the actual values. So what is that, Ante? That's where your new rule comes into play, which is known as Born rule. We will call it as Born rule. Okay, these are very important topics. Now, yes, this is known as a Born rule. So normally we found the inner product of two quantum states. Yeah. So normally we found the inner product of two same quantum state. We got one. Very cool. We found the inner product of two quantum states, and we got to know that that is a probability of the state changing from psi to phi. But what is the actual value? How can I find the actual value? The finding of the actual value is Born rule. Now, before actually going to Born rule, you should know something about measurement. There is something called as measurement. Let's keep a hashtag measurement. This measurement is completely different from the measurement which we actually see when we are dealing with physical computing. Hello? Yeah, okay, sorry. So now, how it is exactly different? Simple deal. In yesterday's session, yeah, in yesterday's session, I have clearly mentioned about something called as if you measure a superposition state, it will be decomposed to one of the base state. Remember? Did anyone of you try to ask me how? You guys simply are concerned like, okay, that's it, end of discussion. Okay, normally that's it, end of discussion only. Why? Because it's a physics property. But yeah, normally physics means we can't say how. We simply can define them in mathematical way. That's it. Okay, if I just if I drop this, it will fall down. How it falls down, I can't say, but I can define it. It's a physical property. It's gravity. I know it's gravity, and I can write the gravity in a mathematical ways. Similarly, this measurement concept, where a superposition state, when measuring, decomposes to one of the base state, can be defined in a physics way, or I can say quantum mechanical way, mathematical way, or whatever. Okay, and that is the entire deal behind it, and that's where your Born rule and your measurement theorem, everything comes into play. Okay, now, so in this measurement concept, we are actually seeing how measuring a quantum state. Now just listen this. One more thing before actually going into measurement, just keep this in your mind. పక్కన బాక్స్ చేసుకుని రాసుకోండి కావస్తే if you want. Every quantum state, we will represent it in a form of superposition state only. Now you may ask, like, if I represent it in the form of superposition state, so every qubit should be 0 and 1, right? But in yesterday's session, I have mentioned one thing. It can be 0, it can be 1, and it can be 0 and 1, I told. Okay. Now, if that is true, then how is this one possible? Simple. It all deals with the what can I say? That equation, that qubit equation. Every quantum state, I will define it in this way only. Every quantum state I will define in this way only. Okay, I won't change it. I will define in this way only. But if it is a zero state, if it is state 0, I will be like beta equal to 0. That's it. And if it is in one state, I will simply be like I'll make if 0. I'll simply make alpha equal to 0 if it is one state. That's it. Okay, but when I'm actually defining, or when I'm actually calculating at that point of time, I will definitely define it in this way. That's a rule. Every quantum computation or every property or everything, I will definitely define it in this way only. Okay, so in yesterday's session I have mentioned it can be 0 state. So I cannot define like this. No, I cannot do it. Okay, so if I want to define, I will write like this, and I will make beta equal to 0. If I want it to be a what can I say, 0th state. If I want it to be in a 0th state, I will write it like this, and then I will make beta equal to 0. Getting the point? So that's the main thing. So keep this in your mind. It is not like you can make like direct the psi equal to 0. No, you cannot do that. Okay, every qubit you should represent it in a superposition format only. And if it is in a zero state, just make beta equal to 0. If it is in one state, just make alpha equal to 0. That's it. Okay, but defining should be in, what can I say this as, superposition state only. Got it? This is a main deal. Now we can actually go to measurement. Yes. So now we can actually go to measurement. Now, so let's go back to the yesterday's thing only. So I hope you guys wrote it in a side top left box or top right box. Now let's come to the actual stuff. Now, in yesterday's session, I have mentioned one thing. Let me just revise it off. I already revised it right now, like 10 minutes back, but again, I will say it once more. That is, when you measure a quantum state, this will be decomposed into, this arrow mark signifies decomposed, let us consider, into one of basis state or one of the base state. Okay, basis state, they are different words. Okay, let us consider like this. This is the entire thing. How? Like, not like how I can just show it. Very simple. Okay, very direct way. Whenever we measure something, the process of measurement, like if you're measuring something, that means what you're doing, you are doing some operation out there, yes or no, if you want to measure something. So let's go to the Schrodinger experiment. So you want to measure the state of the cat, meaning you want to see if the cat is alive or dead. So just by sitting, can you say like it's alive or it's dead? No, you are going and you're opening the box, meaning you are doing some work. Okay. Similarly, if you want to take something, if you want to capture something, if you want to measure something, like for example, if I ask you the capacity of water inside this bottle, you'll pour it in a funnel or something and then you'll see the markings and then you'll measure it. Okay. So you are doing some operation out there. Okay. And when it comes to quantum, the measure, that measurement, we'll call it as an observable or an observer or anything. Use that word, Anma. Whenever, yeah. So whenever I mention something about measurement or something like that, sorry, whenever I mention measurement, it is that I am talking about something known as an observer, or I can say excuse me, guys, just a sec. Yes, okay. I hope this is okay. Yeah, cool. So, whenever I talk about measurement, I am talking about something known as an observer or observable. Okay, I can simply consider it like this. So now, before even going into this in more detailed way, let us see about one more case which happened in Young's slit experiment. Okay, so that's actually kind of cool. So that's why I will just say it. And I did not say it yesterday just because I want to explain with the concept of measurement. Now, when I talk about measurement, I told that it is an observer or an observable, right? Until we are doing some action, the action which we are doing in order to exactly. Okay. Now, now the deal goes like this. Yesterday, you guys remember Young's double slit experiment, right? When you had a single slit, what happened? You saw a straight pattern. So, which was like this, saying that electron is a what particle or wave? Particle. Now, when you kept a double slit, when you kept a double slit, what happened? You saw something known as an which pattern? What's the pattern called? Inference. Okay, it's known as interference pattern actually. So yesterday did I mention as inference? Huh? Okay, this is known as interference pattern. So my bad actually. Now, so it's in okay. So what is this interference pattern? Simple. The middle guy or the center guy will be very bright, followed by some gap and a semi-bright gap and even small light and it small. Same goes here. Same pattern follows here. This is very bright. This is kind. This is also like small bright and last one is very thin. Okay, like very dim kind of thing. Okay. So this is how it actually works and this is known as an interference pattern. Okay. And an interference pattern is only observed when we are having the input in the form of a wave. Okay. An interference pattern is only observed when we have the input in the form of a wave, thereby stating that electron is a wave. Okay. So if there is only a single slit, it behaves like a particle. But if you are having a double slit, it behaves like a wave. Okay. Now what this scientists think ante, something cannot be in two of the states or something cannot be like two of them. It can be like only one thing, right? So they decided to see how it actually is. Okay. Like they decided to measure it, simply to put. They wanted to see how it actually is. Like because normally when I did this experiment, I did not see the electron. I am simply observing the screen to determine how it is actually. But as in first it determined like a particle, and in second case it determined like a wave. The scientists got confused and they wanted to see how it actually is. Okay, I wanted to simply see how it is actually behaving. So for that reason, in the third round, what did they do is, in a third round or in a third iteration, they did something like this. Same double slit, not a problem. And they attached two cameras. One camera in the first slit and one more camera in the second slit. So this is not a gun, that's a camera. Okay, let us consider that's a camera. Okay, and the same experiment, same gun here, and shoot the electrons. Okay, understood? So they simply attach two cameras at the end of two slits to see how it is actually is. Okay, in order to see how it actually is, they attach two cameras. Now they observed in the screen only two thick lines. They did not observe the interference pattern. So what did they observe? They observed something like this. That's it. So simply saying that electron is a what? At this case, electron became a particle. So this is the actual deal. So what happened here when I did not observe it? That is in the second case. I did not observe it, right? So it became a, what can I say? It behaved like a wave. Completely alright. I got an interference pattern. So I got to know that it is a wave. Okay. Completely alright. Now when I actually wanted to see how it actually is, I kept two cameras at the end of the slits and I repeated the same experiment and I got this pattern telling that electron is behaving like a particle but not a wave. So scientists got confused and that's where here where they told that when we did not keep the camera, it came as an interference pattern. When we kept a camera, meaning technically to speak, when we are observing the particle, it is behaving like a, sorry, when we are observing that electron, it behaved like a particle. Meaning this concept called as observation or observable or observing or measuring is influencing the state of the quantum. So I'll just write like this because I don't know how the state looks like. So I kept like a particle and I kept like this, which determines a particle and wave. Okay, so like two of them kalapunnat. Okay, so meaning in the first case it behaved like a particle, completely alright. In the second case it behaved like a wave, and in the third case it behaved like a particle again. Meaning the measurement what I'm doing, so the main, like the observation is equal to measurement, that's what I told now. So the measurement which we are actually doing is influencing the state of the quantum. Yes or no? Are you guys getting the point? Why? Because electron is a subatomic particle, meaning electron is a quantum state. Okay, And when I'm observing that one, like when I'm measuring that one, that is influencing state of the quantum. Are you guys able to get this one? This one point? So that's where they got to know that observation or measurement has a direct influence in the quantum state. Other way in the so that's why I told like when you measure a superposition state, it will come to one of the base states. So that's the entire deal behind it. Got it? Now, how it actually is happening? What is the mathematical definition of this one? Normally, this is the theory. I hope you guys understood the theory, right? You don't observe it, it will be in a superposition state. But when you observe it, it will simply decompose to one of the base state. Okay? Same two examples. One example is a Schrodinger cat. Second example is this Young's double slit experiment. Okay? You don't observe the electron, it acts like a wave or it acts like whatever it is. But when you observe it, it is decomposing into one of the guy. Are you getting the point? So that's the deal. So when you're measuring it before itself or when you're measuring a quantum state, it decomposes. Meaning measurement has a direct influence on the quantum. Now let's go to the mathematics. How I can define it? Simple. Every measurement. So what happened after the third result of YDSC is that scientists got to understand like if I am observing it, then it is influencing the quantum state. So what exactly is influencing the quantum state? The measurement. Okay. So meaning is when I'm saying that I keep a camera, okay, or I'm seeing or looking at it, it is decomposing my quantum state. Okay. So what exactly is there when we are measuring that it is decomposing the quantum state? That's a doubt which came into play. Okay. I can't simply say like for example, if I look at this bottle falls down, let us consider. That means there is something in my eyes which is influencing the behavior of this thing. Yes or no? Are you getting the point? Let us consider I just looked at the bottle falls down. The meaning goes like this. There is something in my eyes which is influencing the bottle to fall down. So the same thing the scientists also got doubt. Like they just got this doubt. Like what is there in the measurement which is influencing the state of the quantum? Influencing ante asala what is applying on that particular thing? What is influencing its behavior? What is actually happening? And they got to know that when you keep a camera, obviously it takes the pic, it records. Kada? Recording means what? How I can see the part, like why I am able to see you people, or how I can see you because of correct answer. What is that? Because of light. So I am able to observe something because of light. So if you really see, light also behaves like a light is also like a subatomic guy. Okay, and it also behaves like two things, wave and a particle. Remember? So light can be determined as a wave and it can also be determined as a particle. Okay, so what the scientists taught is when I'm actually measuring something, the state is getting decomposed. The quantum state is getting decomposed, meaning something in my measurement is affecting the quantum state. And they taught like the what can I say that the camera is there now. The camera one is emitting certain photons, which is actually influencing the quantum state. That's what they got to know. That's what they taught in the first place. Okay, that's a one of the deal. Now, similarly, if you take any sort of measurement, okay, when I'm talking about any sort of measurement, I can define or I can write my measurement as something called as a Hermitian operator. I can define my measurement as something known as a Hermitian operator. Meaning, when I'm saying that I am measuring something or when I'm observing something, it is a physical entity. Meaning, this can be a light, maybe a pulse, or a energy state or energy pulse or whatever it is, or gravity or noise or whatever stuff it can be. whatever, you can just pull whatever stuff, any physics quantity you can keep. Like for example, these all are used when you're dealing with different type of quantum computers, like superconducting qubits or superconducting computers may we will influence with electricity and stuff. So if you're using the magnetic based things, you will be using with magnetism, the ferromagnetism and stuff like that. So light, you will be using the energy pulses, the laser pulses and stuff. So all defines on that particular thing. Okay, depending on the type of computer, depending on the type of quantum computer which you're using, all these things will be changed, or all these measurements will be taken care of. Okay, so that's the entire deal, which is actually influencing the stuff. So this measurement is actually influencing, and I can define that measurement as a physical entity. It can be anything, electricity, gani, pulse, light, sound, noise, gravity, whatever it can be. Okay, and that physical measurement or that physical entity, I will define it like a Hermitian operator in a mathematical way. In mathematics, if I want to define something in mathematical way, I will define it in the form of a Hermitian operator. So what is this Hermitian? So do you guys listen or heard about Hermitian guys before? Hermitian ante enti? If a matrix A equal to A dagger, or is it equal to A star, I will call it as a Hermitian matrix. Okay, if a matrix is Hermitian, oh sorry, when I can say a matrix is Hermitian if it is equal. Simply to put, there's a basic deal behind it. Okay, you don't need to think anything. That's a very basic deal behind it. Determines conjugate transpose. Okay, simple deal. You don't need to think about it that much, and that's your Hermitian bala thing. Now, okay, I mentioned measurement equal to a physical operator, which is a Hermitian operator. So everything. Now you got to know one thing. Now, right now we are having two things. What is that? First thing is a quantum state, which we are actually going to measure, which is a superposition state, alpha naught, beta 1, whatever. And second thing is a measurable A. Okay, which is known as measurable A, which is a Hermitian operator. Okay, now how it actually influence? Very simple thing. First, I will say the definition or a direct definition. Just keep that in your mind directly. The definition goes like this. What is that, Ante? Whenever A is applied to in H. Okay, what is H? Hilbert space, yes. So whenever you apply a measurable to a quantum state in a Hilbert space, simply to put a straightforward thing, this guy, the state will be projected to one of the eigenstates of A. Simple deal. Just this point is important. One of the. So whenever you are measuring or whenever you are applying a measurable A, measurable called as A, which is measurable, which is a Hermitian operator. Whenever you are applying that measurable A to a quantum state psi in a Hilbert space H, or in order to say very clearly, let us consider a single state, so it will be like C square. Now I can say that this psi state will be projected to one of the eigenstates of A, and this guy will be the one of the basis state I mentioned before. So this is approximately analogous to one of the base state. That's why the measurable thing, the outcome after a measurement will not be a superposition state. The outcome or the output of a measurement will be a measurable state. Got it? So that's a simple deal behind it. Understood? Very simple deal. So that's the reason why when you're measuring something, it will be decomposed to one of the base states. Okay? So in order to say it mathematical way, the bond rule I did not define it yet, right? So I defined the bond rule, but I did not write the expression. So the expression is very simple or very straightforward. Now when I say eigenstate A, I can simply say like this: A AI equal to AI A. Okay, which you already know, the eigenvalues, eigenvectors, you already know na, the same day. Meaning this guy will be converted అని కాదు, but this guy can be transposed or this guy can be reflected in this way, where this is the simply to put the amplitude. And this is the eigenstate. AI is the eigenstate. And a vector A or the operator capital A can have many eigenstates, right? So any vector, I will give you a matrix. It can have any number of eigenstates, right? So similarly, this guy has a lot of eigenstates, out of which only one of the eigenstate is your actual answer. Got it? That's a basic deal behind it. And this AI is AI is the amplitude of it. And if you take the AI square, it is nothing but the probability, which you already know, the quantum things, right? That's what I mentioned, right? Alpha is amplitude, alpha square is probability. The same deal. Now, how exactly it can be determined by bond rule? Ante very simple. If you're taking any state psi, I will write it like this. Okay. Now, if I say it has n states, I can write like this. Okay. Any state. For example, initially 2 base states, but I wrote like this. Let us consider it has n base states. At that time, I can determine like this. Meaning, I can write it like yes or no. Can I write in this way? Simple. Only 2 base states unte idi. Let us consider n states. Okay. For example, if you're having n states, it is like this. So can I determine this n state in this way? Yes or no? Simply addition ko summation is petanta. That's it. I can determine in this way. Now, what is the probabilities? So if I take, these are the probabilities. Yes or no? Are you guys getting it? So why? Because when we have alpha naught plus beta 1, it's nothing but alpha square plus beta square equal to 1. Let us consider like that you are having 5. A1 square plus A2 square plus A3 square up to AN square equal to 1. So that's the same thing which I wrote here, which is the probabilities. Are you guys able to follow this one? Just a mathematical notations. That's it. Now, what I can say is, for example, when I want to mention it in an observable and some in that way, I can write like this actually. I can write the output state equal to summation of I equal to 1 to n, same thing, AI of AI square, AI vector. Okay. So what is phi? Let us consider when you're measuring a psi. So you are measuring it and it gives you phi. Let us consider like that. Okay. Okay, simple deal. Let us consider a very basic thing like this. So our entire concept is I am measuring psi, meaning I am measuring a quantum state psi with an operator A. Yes or no? So now when I am measuring a quantum state psi with an operator A, that will convert. Obviously that will convert. Ice cube on the temperature event, it will be converted to water, right? Same thing. State keep a measurable, it will be converting. Let us consider the conversion is to phi state. Psi to phi. Now, if you remember, what is this thing? What is this defined? Kanpistundi? Okay, sorry. What is this defined? Okay, so it's my bad. I just need to. What is this defined? Probability of psi changing to phi. Okay, very simple deal, direct deal. Now, this is phi, right? Now, if I want to say that, now the bond rule comes into play. So the bond rule says that AI can be written as AI. That's it. Okay. So I can say AI can be written as AI, like AI inner product of psi, meaning the state or the inner product of psi converting to AI. Now I mentioned one more thing. AI is what? Amplitude. Exactly. It's an eigenvalue, or I can say it's an amplitude. Okay, that's what I mentioned before, right? Like top ikkada untadadi notes lo. So that is amplitude. So that's why I also mentioned this particular thing equal to 1 అని కూడా రాశాను. Why? Because amplitude square చేస్తే it's a probability that's equal to 1. Now AI is written as this thing according to Bond rule. AI can be written as this particular thing according to Bond rule. Now, oh sorry, it's I can write it like CI. CI. CI can be written as this particular thing in Bond rule. Now, okay. Now, if I'm mentioning the probability, it's nothing but CI square, right? So if I take CI square, I can write it like this as well, which is analogous to looking like this. So thereby, this gives a probability of psi giving an output AI. Got it? So that's a simple deal, and this is how the decomposition actually happens as per mathematics and stuff. Otherwise, so anyway, this entire notes will be provided to you so that you can see all the stuff here and there, and you can just wrap. Okay. So yeah, I would like to conclude till here for this thing. So we'll be having one more thing later, like in after some time, I guess. So I'll just conclude till here up to the measurement. So just take a revision and stuff like that. Cool. Okay. Thank you so much, everyone.
It is such an incredible session, sir. Thank you so much for such an insightful session. We have a thank Dr. Jnan Yalla for guiding us the fascinating world of quantum mechanics so clearly and very patiently. We started with the basics, and it was an amazing start to see that you don't need to be a physics expert to be a quantum enthusiast. It's just a curious mind itself. And we got to peek into the language of quantum mechanics, like the bracket notation and most. But today made that really made sense. The most exciting part is understanding quantum states and superposition. How a state can exist as a mix of zero and one absolute measurement. And speaking of measurement, the FEST experiment perfectly showed how observation itself changes what happens in the quantum world. That really made us stop and think for a while. Thank you, sir, for making such complex ideas feel accessible and fascinating. We really appreciate your time, patience, and the way you took the session. Let's give another big round of applause for the amazing session.